Përshëndetje Qëndrem,
Përshëndetje Hamdi.
apo më dëgjon?
Po të dëgjoj dhe po
Ah,
të dëgjoj dhe po të shikoj.
mirë shumë.
A je mirë?
Mirë, mirë. Se që
Qysh
fje?
po qysh po kalon në edhe unë mirë Hamdi. Qysh po kalon në Warwick?
Mirë. Po i lodhën.
Pse?
Um, pak si shumë punë.
A
Um,
ke edhe angazhime me jap mësim ose me grade ose diçka?
po, kam. Këtë vit kam marrë përgjegjësi nga më të ndryshmet. Kam qenë
Aha.
si për 2 landë, andaj we have some kind of supervisions. I kemi
Aha.
për shembull dy grupe nga 5 studenta dhe takohesh me ta
Po.
çdo javë vitit parë dhe ju ndihmon
Po.
mos më dekuraju.
Gjë që unë e kam propozuar në fakt edhe në departament tonin, po nuk e kemi implementuar asnjëherë sepse meqense se jemi departamenti i vogël, kemi hapësirë që secili të vitit parë më marr ka 5 studenta, mos më taku të tërmësh çdo javë, po mjafton më taku një herë në muaj, edhe është shumë orientuese, shumë lehtësuese për studentët. Po,
Definitivisht. Unë jam kënaqur vete. Në fakt, ata pojnë edhe zyra të shtëpis, unë ja kontrolloj, nëse ndaj na diskutojmë.
po,
Më thënë, mënyra se qysh i qosesh problemeve ka shumë rëndësi, sidomos nëse je vitën e parë, e me pas dikën që ka pak eksperiencë në atë
pikërisht.
pjesë, është ndim kështu e papame. Jam shumë i lumtur se do të thënë 9 persona nga 10 gjithmonë
Mhm.
kanë ardhur gjatë gjithë vitit, kështu që pjesëmarrja ka qenë 90%, kështu që shumë mirë.
Shumë mirë. Shumë mirë.
Ti me punë, apo lodhesh?
Me punë ka pak që unë qëtash e pata do algebër lineare mbaj këtë semestër për vitin e parë. Çado që nuk jam shumë fans i këtyre gjërave, i shkruajta do shënime për me përgatit. Po e kam një ide, fola me Uranin para disa dite, sado që je shumë i zonë, mendova me qenë një grup, muj me qenë 3, 4, 5, nuk është problem, me bë një bashkëpunim online, ku mundemi me shkru diçka, mundet me qenë për studentët tonë, në qoftë se secili ndihmon ka pak, është më lehtë. Po të kontaktoj për këto në një, domethënë, rast tjetër të veçantë, që mos me
Patjetër.
se po, domethënë ideja është që me shfrytzu faktin me qenë se jemi domethënë sado që nuk jemi ndoshta të fushat identike, po me bashkëpunu mundemi me shtu diçka. Ai s'ka nevojë me qenë fizikisht në një vend.
E vërtet. Po, ide shumë mirë.
Kontaktoj ndomas. Përshëndetje, sapo na u bashkuan profesori Bujar Fizullahu dhe profesori
Përshëndetje.
Haxhi Beqiri. Përshëndetje të dashur koleg. Qysh po shkojmë punë me mentor, që na u bashku Islami.
Përshëndetje Islam. Mirë, kryesisht tash e kam projektin e parë të doktoratës edhe shpresoj që nesër 2 slide të fundit i tregoj pak a shumë çka po bëj.
Përshëndetje Islam.
Përshëndetje Islam. Mirë kryesisht, po ende nuk kam përfundu krejt projektin, po shpresoj ka fundi vitit ndoshta.
Okay. A do në Kosovë vizit?
Po shpresoj gjatë verës.
Nëse kur të vjen, tregon, të lutem, edhe takomi.
Patjetër. Me shumë qef. Faleminderit.
Po presim edhe një 2 minuta ndoshta, apo?
Po, patjetër.
Është diçka të ndodhë, telefonin e kam 1301, kurse kompjuterin 1300. sa do që 2 të duhet me qenë, kurse orën e kam 13:02. Okej, këto
A
moment
ka
i gati.
lokacionin e njëjtë, ora
Faleminderit.
telefoni edhe.
Ora mund të të qenë nga njëherë do pësot bateria, po të paktën telefoni
Mhm,
edhe kompjuteri të duaj.
mhm, mhm.
Okej. Për në bashkuat edhe profesori Menderes, profesori Ender,
Përshëndetje.
me profesorin Menderes jemi një komision që është
Mhm.
mbrojtjes masterit, është një student të Armendi, e kështu që me mbarimin e seminarit do ta lëshojmë së sallën me njëherë. Okej. A mundemi gradualisht me fillu, Hamdi? A është okej?
Patjetër, patjetër.
Okej.
Nëse mundesh me mbo host.
Po, do të bëj absolutisht.
Ah,
Bëj, ose nëse të bëj
ose
host,
co-host, ose co-host.
atëherë
Sorry.
po, ose veç të lutem nëse do të bëj co-host
Mhm,
bashkë një koqirë. Veç ka njëherë është e mund që dalin ty tash ata që dojnë me orë sepse
mhm.
presin në korridor në sallë pritjes. Okej. A mundemi? Okej, great. Shumë mirë. Atëherë, më lejoni që gradualisht ta fillojmë seminarin. So, I have a special pleasure to introduce our next speaker, who is actually the last speaker for this academic year, Hamdi Dërvodeli, who was our student at the University of Prishtina, and we're very proud of that, and who is now at Warwick. Hamdi will be speaking about what is tropical geometry. So, Hamdi, thank you so much, and the floor is yours.
Thank you, Chandram, for having me speak today. And as the last speaker, thank you also for organizing the seminar. I enjoyed it very much, and I hope it runs for many years to come. Okay. Now, without further ado, as the title suggests, I am gonna try to give a gentle introduction to tropical geometry, and so what is tropical geometry essentially? The slogan for this talk, it's going to be that tropical geometry is a combinatorial shadow of algebraic geometry. And the goal overall is that we want to solve problems in algebraic geometry using combinatorial techniques, because sometimes that's just the easier thing to do. And in this picture, on the left, you see an elliptic curve that is the solution set of a polynomial with 2 variables in degree 3. These are called varieties in algebraic geometry. And to the right, I have its shadow in tropical geometry, which is usually called tropical elliptic curve. And we are interested to go from the left side to the right-hand side. And there's a process that does that, which is encoded with this arrow. And sometimes when we do that, some of the information is preserved, making our life a bit more easier. For example, this is an elliptic curve, so it's a dimension 1 variety. So that information of dimension, you can see it from these like half rays going up to the right and down. And this elliptic curve is also defined by a degree 3 polynomial, as I said, in 2 variables. So you can see 3 rays going up, down, and to the right. Moreover, you've got, an elliptic curve is topologically a torus that you can think of as a donut. So it has a hole. So we say that's genus 1. And that information of the genus, you can see it in this cycle on the right here. Before I continue with my next slide, I just want to say that, this approach that we're taking is the embedded approach. What that means is that I take these shadows of some varieties living somewhere. We're interested in maybe varieties living in an affine space, or the algebraic torus, or the projective space, and so on. But rest assured that there is tropical geometry which uses the non-embedded approach. So yeah, okay. From this slide, we get that tropical geometry is somehow a part of algebraic geometry. However, I want to make a disclaimer, because it's not just that, it's a much broader field, and it has many applications inside and outside mathematics. Some of the examples that I can mention is in economics. Paul Klemper, a professor at the University of Oxford, he invented some pricing auctions to save the Bank of England from bankrupting during the financial crisis in 2007, using some methods from tropical geometry. And then optimization. In the 80s, the Dutch railway subway system was designed using methods in tropical geometry. You've got applications as well as in machine learning, neural networks, and RaLU activating functions. That family is essentially tropical rational functions. And you've got maybe phylogenetics, which is a field of biology which studies essentially the evolutionary history and like the relationships among organisms and living in it. And tropical geometry offers a good representation geometric model for that. So this is an overview that tells you that, you know, you can see it as a part of algebraic geometry, but also it has much more to it. One way of thinking about tropical geometry is the algebraic geometry over the tropical semi-ring. We do algebraic geometry over a field, usually, like let's say complex numbers. But what we do in here is we don't take a field, but we take what is called a tropical semi-ring. That is the sets R union infinity, together with two operations: tropical plus, which is the minimum, tropical multiplication, which is the usual plus. And we call it R bar. And whenever we do arithmetic in here, we have to do these kind of calculations. Like, for example, 5 tropical plus 9, it's going to be the minimum of 5 and 9. It's going to be 5. 3 tropical multiplication 9, it's the usual 3 plus 9 is 12. Two things to notice here is that tropically, infinity plus x is always going to give us x. So infinity, it's going to be the additive identity here. And 0 times x tropically, it's going to give us x. So 0 is the multiplicative identity. Together with these two, we know as well that tropical addition, multiplication satisfy, well, it's associative, commutative. The tropical multiplication distributes over tropical addition, as this example shows here. But the thing to note is that there's no tropical subtraction. So there's no inverse to the tropical addition operation. So whenever I look for solutions, y tropical plus x equals to infinity, in where x and y are real numbers, there's no solution to that. This makes R bar with these two operations a semi-ring, not a ring. Okay, good. And now, instead of a field, we have a semi-ring. In algebraic geometry, we care about polynomials over a field. And now, naturally, we care about tropical polynomials over the semi-ring. And what are those? They are just going to be piecewise linear functions with like a finite number of parts, and they form a semi-ring. It is denoted by r bar adjoint x1 to xn. And this is one example, x1 squared, tropical plus x2 times xn. One example is if I take x to the fourth plus x squared plus 1 times x plus 4 is a tropical polynomial with one variable. In the classical setting, that will be the minimum of 4 terms. Like, for example, x to the fourth is x tropical times x, tropical times x, tropical times x 4 times. That's 4x. And similarly, you do x squared to 2x and so on. And if I plot the graph of this tropical polynomial, it's this piecewise, it's this piecewise linear function in red with these points, like black points, where it breaks linearity, essentially. And now we want to know about the zeros, or like where polynomials over fields vanish in algebraic geometry. Now we want to know where do these tropical polynomials vanish, or what is the zero locus, or what is the zero set of a tropical polynomial. This definition is what is called a tropical hypersurface when you have just one polynomial. So if I have a big F, a tropical polynomial, I define my tropical hypersurface, V of F, as a set of all W in R bar to the N, such that F takes the value infinity at W, or the minimum in F of W is achieved at least twice. What do I mean by at least twice? That means the minimum is achieved at 2 different monomials. We will see in a second why is this a good definition. But an example for that is a standard example in tropical geometry, which is called a tropical line. It's if I take the polynomial x plus y plus 0 tropically, and I try to compute this v of f, it's going to be just points x and y in r bar squared, such that f of w is going to be infinity, or the minimum in the minimum of x, y, and 0 is achieved twice. And when does that happen? Well, that happens whenever I have x equal to 0 less than y, because I would have that the minimum is achieved at 2 different monomials, x and 0. So that would be this line over here. And similarly, x equals to y, less or equal to 0. The minimum is achieved in x and y, so it's this line here. And the last one, y equals to 0, less or equal to x, which is the positive x-axis. Okay. More examples, just to see how does this definition work. This is an example of a tropical plane. My polynomial is x plus y plus z plus 0. That's classically the minimum of x and y and z and 0. And it looks like this. It looks like this. And I've got a point here, like point A in red and point B. And you can see that if I plug in, like this point A is in the tropical hypersurface because f of 0 to 3, it's just going to be the minimum of 0 to 3 and 0. And you see that the minimum is achieved twice at x and at 0. But this point B in the lower part of the positive orthant, 3, 3 minus 2 is not in the tropical hypersurface, because when I evaluate my function, my tropical polynomial at that point, I get that the minimum is 3, 3 minus 2 and 0. And you see that the minimum is minus 2, and it only happens once. So that's not part of my tropical plane. Similarly, this is the tropical elliptic curve from the very first slide that I put in the beginning, and you've got an equation like this. What you do is you turn your tropical addition into minimum, your tropical multiplication into plus, and you find out the minimum of these bunch of functions, and it turns out that it's this really nice graph like this. And again, similarly as before, you can see that the point 3, 2 is in the tropical elliptic curve because the minimum is going to be achieved twice at these monomials, 1 plus y and 3. Whereas the point in blue, b, 2, 1, the minimum is only achieved once, so that point is not in my tropical elliptic curve. Something a bit more complicated, maybe, which is the tropical quadric. So I've got a quadric in free space, and its tropical hypersurface looks something like this. Okay. Before I start and tell you how is this all connected with algebraic geometry, let me just check what time is it. Okay. Let me. Yeah. Sorry. So let me tell you about tropical quadratic formula. In classical algebraic geometry, we all know the roots of our quadratic equation, right? And those roots are precisely a hypersurface. They are like solutions of a polynomial with one variable and degree 2. Now, what we do is we call tropical roots of this tropical quadratic polynomial as exactly the tropical hypersurface defined by f in this case. And if you do this calculation, that means I turn again tropical plus into minimum and so on. I get the minimum of 3 terms. I've got 3 lines in here, and they intersect in 2 different cases. Like the first case is if maybe if b is too large, you can see that this line y equals x plus b is like above this yellow point here, the intersection of the other 2. And in this case, we say that c minus a over 2, it's it's a tropical root of f. Similarly, if b is small enough, you can see that these 3 lines here that intersect in this sort of like 3 pieces, red pieces, and you can see that as well that the minimum is achieved twice in these points, and you denote them by like c minus b and b minus a. And the one thing to note here, though, is that 2b is tropically b squared, and a plus c is tropical a times c. And we have 2 cases where we compare b squared and a times c similarly as we do in the classical setting. So suddenly we care about the discriminants and the relative size of b squared and a times c. Where did the 4 go? Well, maybe we'll see that in a bit, but this should not be surprising. Yeah, okay. Yeah, one last thing is that whenever I have polynomials in a ring, I've got ideals in a ring, and if I have polynomials over a semi-ring, the ones that we care about, do we have ideals of a semi-ring? That is a question that, ideals are defined over semi-rings. They're in the same way, they're closed under the tropical addition and closed under the tropical multiplication by tropical polynomials. And you can define the tropical variety of an ideal by intersecting all tropical hypersurfaces V of F, where F is in your ideal in the tropical semi-ring. Yeah, okay. And now I want to tell you how is this concept connected to algebraic geometry. That's one. So essentially, where are these combinatorial shadows coming from? And secondly, what kind of information is preserved and what kinds of information are not preserved? And if time permits, I will tell you also a connection with matroids, which somehow makes our life easier, especially in the research that I'm doing right now. So without further ado, let's I continue with the second part. And this connection is done using two main things: valuations and tropicalizations. What is a valuation? Well, if I have a field K, a valuation on our field K is just going to be a function from K to R union infinity, which satisfies three properties. It sends 0 to infinity. It sends a product A times B to the sum of their valuations. And the valuation of the sum of two field elements A, B is greater or equal than the minimum of the valuations of each of them. If you want some intuition about valuations, you can think about the log, like the logarithm, right? I mean, they like the property 2 is satisfied, and the property 3 is like with max instead of min. But we will soon find out that that's also not very different from what we're doing. And some examples that we use repeatedly is, well, the trivial valuation. I send everything to 0, except for 0 itself, because it goes to infinity, right? That's the trivial valuation. The second example is the p-adic valuation. If my field is the rational numbers and I've got a prime number, then I know I can write down every rational number as p to the k times a over b, where p does not divide either b or a. And I just extract the highest power of p in there, which is in this case k. For example, the valuation, the two-adic valuation of 4 over 7, it's the two-adic valuation of 2 squared times 1 over 7. That's just going to be 2 because the highest power of 2 is 2 again. The valuation, the three-adic valuation of 5 over 7, in a similar way, the highest sort of power is -3. So the valuation is -3. In tropical geometry, we often use the field of Poisson series. It's a very nice field. Its elements are going to be formal power sums of this form, C1, T2, A1, and so on, where my coefficients C1, C2 are non-zero complex numbers, and A1, A2, and so on are rational numbers with common denominator. And what I do, my valuation is just going to send this power series to the lowest exponent in the expansion. For example, the valuation of pi is pi times t to the 0 is 0. the valuation of this expression over here, as you can see, is -3. Another example is the valuation of this rational function. If I turn this into a series like this, I can write it down as 2/3 t squared plus some higher order terms. So it's just going to be 2. Like the valuation is going to be 2. Now that we have those examples of valuations, now we turn our focus to tropicalization. And what does that do? This is supposed to be the arrow that that was in the first slide. And if I have a function, if I have a polynomial with n variables written formally like this, with this multi-index notation, the tropicalization of my polynomial is just going to be a function from r to the n, the number of variables, to r, that sends every w in r to the n to this expression, which is tropical sum, take the valuations of your coefficients and turn your multiplication into tropical multiplication. Essentially, we should think about this tropicalization as a rule, where I turn the normal addition to tropical addition, multiplication, multiplication to tropical multiplication, and I take my coefficients of my polynomial to their valuations. For example, if I have a polynomial 1 times x minus 1 times y plus 1 in the field of in the ring with 2 variables over the field of Poisson series, then what do I do? Well, I take the valuations of the coefficients, as you can see in green, in pink, and blue, and then I take I sum over the exponents of the variables. In this case, x has like this is x to the 1, y to 0, so I've got 1, 0 here, and I multiply that with my w, which is w1 and w2. So when I do this, I obtain this minimum of w1, w2, and 0. And now we want to talk about tropical hypersurfaces. And again, like before, the tropical hypersurface of a polynomial f, it's just going to be points in Rn such that the minimum in trop f of w, like we did before, is achieved at least twice. And this is nothing new, because, for example, if I take x minus y plus 1, we did that just before. That was the minimum of w1, w2, and 0. And what was this minimum? This was exactly a tropical line that we discussed in the very, very first example. And this is like a notation. I sometimes we don't want to really write trop f of w. We just write down trop of f in this way, so that we don't necessarily write a lot of things. And with that notation, you get that the 0 set of the tropicalization of your polynomial is just going to be the tropical hypersurface trop v of f. So okay, more examples just to make us sort of a bit more familiar. How did these look like? If I get 3x plus 5y plus 7z plus 1, for example, here, the rule of tropicalization was what? I take my coefficients, 3, 5, 7, and 1. in those coefficients in Q with a two-adic valuation, they turn into 0, because the highest power of 2 in 3 is 0. Same for 5, 7, and 1. And trop of F would be just the tropical plane that we discussed before. Another example, and again, we take the field of Poisson series. Again, we take the coefficients 3t. That has valuation 1 because t to the 1 here, and then x squared turns into 2x, and so on and so forth. And the picture that we obtain with this specific type of valuation is this. Sorry, I keep doing that. Okay. But where is that combinatorial shadow that we've been talking about? And that is Kaprano's theorem, and that says, well, under some conditions, like if my field is algebraically closed and my valuation is non-trivial, if I have a polynomial in the Laurent ring of polynomials, so I'm allowed to have plus minus powers of my variables, then what this theorem tells you is that you can obtain your tropical hypersurface by taking the closure of point-wise or coordinate-wise valuations of points in your variety V of F. And this is where this is what is your combinatorial shadow. It's like it's enough for you to take points in your variety and then take the valuations of the points individually. You take the closure with respect to the Euclidean topology and you obtain your tropical hypersurface. And if we take the example from before, x minus 1 plus 1, what do we do first? Well, the points of my variety are of the form z plus 1, because they satisfy x minus 1 plus 1 equals to 0. And a little bit of work, you take the valuations individually, and you divide this into cases using properties of your valuations in such a way that, for example, if the valuation of z is bigger than 0, I got this like yellow positive x-axis, and so on and so forth. So it's another way of characterizing your tropical hypersurface using the points of your original variety in algebraic geometry. Okay, and you do this not just for polynomials, but you do this for ideals of polynomials, right? That means if I have an ideal in the Laurent ring, and I have a valuation there, maybe I consider the variety of that ideal in the algebraic torus, which is this k star to the n. This is just a way to say I'm interested in the solution set of my polynomials, but I don't want them to be 0. And once I take that variety, what is a tropicalization of my variety x? Again, as in the classical setting, you care about the common solution. So you take the intersection of your tropical hypersurfaces, so trop V of F, and you let F run through all the ideal I. One example is maybe a simple one. I take the field of Poisson series. I take the ideal x plus y plus 1 and x plus 2y. So it's generated by two sort of polynomials, linear polynomials. the variety is just going to be a point, right? It's going to be the solution of x plus y plus 1 equals to 0 and x plus 2y is equal to 0. That will be minus 2 and 1. That is it's not, neither of the coordinates are 0, so that's part of g squared. So the torus, it's just k star squared. And what is the tropicalization of this variety? Again, now, not from Caprano's theorem, but from a generalization of Caprano's theorem that says that you can carry on the same statement that before. You can do it for ideals as well, which is called the fundamental theorem. And it's enough for me to take the valuations of -2 and 1. And since we're living in the Poisson series, the valuation of -2 is 0 because it's a constant, and the same thing for 1. So the valuation of 1 is 0. Okay. Now we're gonna sort of give one example of how you construct tropical hypersurfaces theoretically. There are ways that you can do it computationally as well, which is normally the easier way. But for the sake of just demonstrating, I have chosen this example, the very first one, the tropical elliptic curve. And as you can see, I've got my tropical F, and I form the Newton polytope of F. What does that mean? That means I record I take the convex hull of the exponents of my variables. In this case, we've got 10 points. And let's say, for example, the point 30 corresponds to the monomial x to the third. The point 12 corresponds to xy squared. And the convex hull means you just take the smallest convex set containing all the points. So that's step 1. And step 2, you see the coefficients and you lift them accordingly. For example, you see these red coefficients, which it's 3. I lift the points, let's say 30 to the height 3, like I did on the right here. And the coefficients of x squared y, for example, it's 1. So I lift the point 2, 1, 2, 2, 1, 1. Once I do that, and I've got my lifted points, see, like the red ones and the black ones, I take the convex hull again, and once I do that, I look at the lower faces from a point below. This is a lower face, this triangle in black, but like, for example, this one is not, because if I see it from below, I don't really see this area, and this process I do it for every lower face, and I record whatever I see in here. For example, for this lower face, I will record this triangle over here. And I do this for all the lower faces. I obtain this triangulation of my Newton polytope, and then I've got 2 ways to obtain my final tropical curve from this. Well, I take the inner normal fan. That means I take the inner normals of these triangles inside, and I connect them in this way. And if I want to work with what is called the max convention, I would just leave it at this. This would be my tropical hypersurface. If I want to work with my tropical semiring with a min convention that we set in the beginning, I just take a point x here and I send it to -x. So I sort of like flip it, I reflect it. And this would be your tropical hypersurface that we obtain. Okay. now we kind of ask the questions like we said before, what kind of information is preserved? And one question is dimension preserved during that process of tropicalization? And the structure theorem in tropical geometry, among other things, tells you that the answer to that question is yes. So if I take a variety of an ideal, and I see the dimension of my variety here on the left, and I see the dimension of my tropicalization, then they will be equal. Note that I haven't really told you what is the dimension of my tropical hypersurface or my tropical variety, but I will tell you in these two examples below. If I take a line, y equals x plus 1 here, the dimension of the line is 1. If I tropicalize that, I get the tropical line that we all saw looks like this. And what this theorem tells us is that dimension is 1. And what is dimension in this setting? Well, it says you see the maximal kind of cones, in this case, are like these half rays. And a dimension of a half ray is defined as the smallest sort of affine subspace that contains it. In this case, a half ray is contained minimally in like a line. So, and the dimension of a line is 1. So the dimension of my tropical line is going to be 1. And the second example is if I take a plane in the classical setting like this, the dimension is 2. I tropicalize it, I get my tropical plane as we saw it before, and the dimension of this tropical plane is 2 because this is the maximal kind of cone, and you know the smallest affine subspace that contains this kind of shaded yellow shaded area. It's going to be a plane, and that's of dimension 2. Okay, and this is good news. But what about the other question, which was, is the genus preserved? And the answer is that that's not always the case. And in here we've got two examples. You've got an elliptic curve given by a Weierstrass equation in the general form, y squared minus x to the third plus ax plus b, the valuation b, and if you do the same procedure that we did a couple of slides ago, based on this condition, you'll find out that your tropical version of this curve, it's going to look like this, and there's no cycles in here. So in that case, we say that the genus of a tropical hypersurface, a tropical curve, is 0 if there's no cycles. On the other hand, on the right, you've got an elliptic curve in this honeycomb kind of form, and I've got my coefficients a and b. And if I have this condition, whenever my valuation of this coefficient a is strictly bigger than 2 times the valuation of the coefficient b, then when I tropicalize this curve, I get 1 cycle here, as we all saw. In our examples before, our a was 3 and our b was 1. Well, I mean, that means, sorry, the valuation of a was maybe 3 and the valuation of b was 1. So this condition is satisfied. Yeah, okay. How are we doing with time? Okay, 15 minutes. Let's see. So now that we've seen this connection with algebraic geometry, and I raised the question of the genus, I did that because I want to have a smooth transition from that part of algebraic geometry, that part of tropical geometry, with my current research here at Warwick. And essentially, my research right now is trying to answer the question, how do I get a formula for the genus somehow? And the answer, more or less, lies down to connecting my tropical varieties to other objects, which are called matroids. And you can think of matroids as generalizations of linear subspaces, maybe graphs. And in here, I've got one definition, which I use to illustrate this concept, and it's using the concept of bases from vector spaces. So a matroid essentially is a finite set E, like with n elements, 1, 2 to n, and a collection of subsets of E called B. And these elements in this collection are called bases. They would satisfy two things, two axioms. This is supposed to remind you of the basis of vector spaces, essentially. Well, first of all, it's not empty as a collection, so we have bases to work with. And if I got two bases that are different, A and B, and I've got an element which is in one base A, which is not in B, then what this basis exchange property tells me is that I can always find an element in the other base B, which is not in A, such that whenever I take away small a from my base big A, and I add my element B, I create a new basis. That's essentially what a matroid is. And one example would be maybe a vector matroid. If I take a matrix and I consider the sets of columns, so that's E for us. That's my ground set E. So 1, 2, 3, and my basis is going to be the maximal independent columns of A. In this case, it's just going to be the column 1 and 2. And you have, so this is what's called a vector matroid. In matroid theory, you've got a lot of rich theory about matroids. One of them is like invariance, and the simplest invariance, and the simplest invariance of a matroid is the rank, which is the number of elements of a base. So for any two different bases, they have the same cardinality, and that's called the rank of a matroid. In this particular example, the rank of my matroid is just going to be, as I said, the cardinality of 1, 2, which is just 2. But in this particular case, that means the number of maximal independent columns, and that's just the rank of the matrix A. The last two slides are meant to, okay, so I've got my matroids. I've given you a vector matroid, an example, and I'm going to give you another matroid, which is very important, which is the uniform matroid. And you can think of it as like a rank K matroid on n elements. For example, U23 would be a matroid with a ground set with 3 elements, 1, 2, 3, and rank 2, which means I get 2 element subsets. So 1, 2, 1, 3, 2, 3. And U34, for example, you've got a ground set E with 4 elements. You've got the bases are 3 element subsets of E, which is 1, 2, 3, 1, 2, 4, and 2, 3, 4, and the rank is 3. And these kind of matroids are really interesting because they relate. I mean, matroids in general relate to tropical geometry with something that is called Bergman fans. I'm not going to tell you what Bergman fans are, but what I'm going to tell you is that the Bergman fan of the matroid U23 upstairs is going to be my tropical line. The Bergman fan of U34 is going to be my tropical plane. And once we see that the Bergman fans, are essentially tropical hypersurfaces, then my research, well, the result that we have at this point in time is essentially saying matroids know about tropical varieties, and we care about information about tropical varieties. And the actual statement of the result is that for large enough degree D, like I can always find such a large degree D such that when I take my tropical variety here, and I, with some injective function that I'm not going to tell you what it is, I can express it as the intersection of the Bergman fan of some matroid MD, which depends on this index D here, which is large enough, with some linear subspace, which is like a row space of some matrix. And what is interesting about this result, I think, is that this tells you, if you start with the tropical variety here, I can find a degree D somewhere and a matroid that knows about it in a way that whenever I intersect with some familiar subspace, I will always get back to my tropical variety. And this prompts the question that I'm currently trying to solve, which is, well, if this matroid MD knows my tropical variety, then it must know other things as well. And I ask, where is this matroid MD hiding the information about the genus of my tropical variety? And more than this, what else does this matroid know about my tropical variety? And that is more or less the direction of what I'm doing right now, and that will be the end of my presentation for today. Thank you. If you have any questions or comments.
Thank you so much, Hamdi. Faleminderit shumë. Faleminderit tani Islam.
Yeah, I had a small question. So for the tropical semmering, you usually use R, and I guess it's obvious that you need the order for the minimum and need to play well with additions. But are there any other rings in use for other versions of tropical geometry, like Z or...
Interesting. Okay, so you want to kind of work with maybe more general semi-rings, I guess. Well, one thing which is interesting is a semi-field, and you can replace that tropical semi-ring with a semi-field, so you can do things with those. Maybe another option would be, as you noticed, like the tropical semi-ring is like additively idempotent, so x plus x is x again, so it's like x squared is x. So maybe you can replace your R with an additively idempotent ring, if that makes sense. Yeah. Maybe those two. Yeah.
Yeah, it makes sense. Okay, thanks for the talk. Cheers.
Thank you.
Okay. Do you have any other questions? If you could go back just one slide, please.
Sure.
Yeah. So, could you tell us just a little bit more over on what is the row space of which matrix, or if you have an example that you've worked out, because I would like to know a bit more.
Yes, of course. Great question. Well, this row space of this matrix is precisely the matrix of the Veronese embedding that I use to embed my variety into a higher space. And so it's like the matrix of the coefficients. Like, for example, if you have x, y, z, and then you send, if the degree is 3, that map is going to be, it's going to send x to like that point is going to send to x3, and then x squared y, x squared z, and so on and so forth. So all monomials of degree 3 in 2 variables, and my matrix is going to be 3, 0, 0. It's going to be 2, 1, 0, 2, 0, 1, and so on and so forth. But the interesting thing about this matrix and this embedding is that so my tropical variety here, it's the variety of some special ideal that we usually call tropical ideals. And a tropical ideal is just taking the tropicalizations of elements in your ideal. But secretly, what I haven't told you is that that concept of a tropical ideal in itself encodes a sequence of these matroids in a way that makes up for the fact that we don't have tropical subtraction. And that's a really cool thing. And it's a very recent, I think, kind of concept. So essentially, tropicalization, matroids, ideals, they're an easy subspace. They're all linked together in such a way that if you give me a tropical ideal, if you give me a tropical variety, hopefully we will be saying things like, great, you tell me that, I find you the matroid, and I find you exactly where the information about the genus is. And this is it. Yeah.
And have you tried to work out some concrete examples where you take, okay, so you already know, for example, the combinatorics.
Yeah, for example, if I take the curve.
And sorry, are you? Maybe I should rephrase it. Are you looking at examples in any dimension, or are you looking at understanding completely things at lower dimensions first? What's your approach?
Oh, I see. Well, ideally, we would want, whenever you give me a tropical variety, ideally, I would want to give you a matroid that knows it. I mean, I can give you that matroid now for any tropical variety that you give me. But also, we want that matroid to tell you much more about your tropical variety. For example, we saw before that sometimes the genus is preserved from classical varieties to tropical varieties. And if we successfully arrive at a conclusion where matroids know about the genus, then you give me a classical variety, I tell you the genus from this very combinatorial matroid fact somewhere. So that's the idea, telling you geometric information about tropical varieties and varieties whenever we can, using combinatorics underlying matroid theory in this particular instance. Does that make sense?
Yeah. Okay. Great. Thank you so much. Faleminderit shumë edhe një herë, Hamdi.
Faleminderit edhe për juve.
Edhe fakt ka plot pyetje, po qartazi do të më lënë për kur shihemi ose do ta vazhdojmë bisedën, për shkak se ka gjëra që lidhen edhe me interesat e mia matematike. Okay. Atëherë nëse
Do you mean toward varieties? Maybe.
Yes, exactly. But not just that, but yes. But yes, if you want to say a word or two about toric varieties, please.
All I'm going to say is that there's a rich connection with toric varieties. And as you know, toric varieties lie in between like algebraic geometry and combinatorics. And there's connections with toric, like tropicalizations like you can tropicalize toric varieties for one, and secondly, maybe if you have a subvariety and you tropicalize it, that will record a specific type of information. It will tell you which torus orbits are going to be intersected by another subvariety, for example, or tropicalizations can offer a very good choice of compactifications, for example. A lot of people are like working in this, so it's very, very interesting, I'd say.
Great.
Yeah.
Okay.
Okay.
So thank you so much. And if we have no further questions, then we and I thank you on behalf of everyone. Faleminderit shumë edhe një herë. Edhe shihemi së shpejti, ndoshta po mendoj semestrin tjetër në seminarin e radhës. Faleminderit shumë Hamdi. Kalosh bukur,
Gjithashtu
suksese.
qëndrem.
Edhe shihemi. Faleminderit gjithëve.
Mira.
Faleminderit
Faleminderit
Islam.
gjithëve.
Hamdi, faleminderit Shëndrëm.
Faleminderit
Gjithë mirë.
profesor Çabel,
Gjithë mirë.
Bujar, Nderes, kisha diku tjetër. Mirupafshim.
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 Ditën e mirë.